So maybe we can start. Adam, tell me how you got into your field. How'd you become a planet hound?
Well, I liked planets and astronomy and science in general ever since I was a kid. So, when I was in grade school, I was really interested in the stars and, I had pictures of the surface of Mars as seen by the Viking landers in my bedroom and that sort of thing.
Right.
When I was an undergrad, I went to Stanford, which did not really have an astronomy program. I majored in physics, but still was really interested and tried to do a lot of reading, and that got me more and more excited about the field.
Mm-hmm. And of course, there were some glorious missions and years for planetary science in those times. It sort of came of age, probably was as you were growing up. Some of the great missions of
That's
the
right.
70s and 80s.
That's right. So, for example, the first one that I really was strongly aware of was the Voyager flyby past Saturn, which occurred in sort of 1981 or so. So I was in about sixth grade, and on the cover of Time magazine was this amazing picture of Saturn, and inside they had all these different pictures of the moons and the rings and so on. And so I was just really excited about that. I cut out all the pictures and put them in this little booklet that I made that I brought to school and that kind of thing. So that really kept me excited for sure.
And that sort of just makes me think of an aside that the pictures from the planetary missions, the Cassini-class missions these days, are so good that some people just think they're fake. I mean, they're so crisp, they're so clear, the patterns are so amazing, the colors are amazing.
But at that time, of course, there was no Photoshop and that sort of thing, so it was much harder probably to fake a picture. So these days, you could easily concoct some computer-generated thing that looks nicely like Saturn, and in 1981, that was not so possible. So there was maybe that much more shock value to the pictures for that reason.
Right. So talk about more of the present day. Is this for the study of the solar system, is this a good time? I mean, are we learning a lot? Are there still some good unsolved puzzles to deal with?
It is. It's maybe what you could call sort of the second major phase. The phase from the early 60s through probably about the mid-80s was sort of the kind of reconnaissance phase, send the first flybys past all the major planets. The Voyager mission is a great example, with Voyager 2 going past Jupiter, Saturn, Uranus, and Neptune one by one. It was our first close-up, high-resolution looks at those planets, especially the outermost ones.
Right.
And since then, we've transitioned to a phase where we're sending repeat missions to some of those same planets. Many missions to Mars, got a second mission right now at Mercury. Cassini is now at Saturn, building on the Voyager experience from before. And so we're now in a period of really deepening our understanding, getting longer time records, imaging parts of the planets we hadn't seen before at higher resolution with much better spectrometers, much better instruments, and finally extending maybe the phase not just into a period of discovery and, oh wow, look at all these amazing things in the solar system, but actually trying to connect those to the science we have here on Earth and really trying to understand the mechanisms and the processes.
Right.
Another thing that is linked up is the discovery of exoplanets, and so this is really bringing back together again the fields of astronomy and planetary science. Those fields, of course, started together and only split apart maybe in the early 60s once spacecraft started to be sent to the other planets. It was only at that time that the type of data sets we were getting for planets really started to differ drastically from typical astronomical data sets.
Right.
So for several decades, the fields were distinct, and now they're being brought back together. And so a lot of the stuff that we are deepening our knowledge of in the solar system has direct relevance to understanding planets around other stars. And likewise, the discovery of planets around other stars, seeing the whole continuum of masses of planets, distances from their stars, different types of behaviors, is forcing us to ask new questions about how the solar system itself formed, the processes happening in our own planets and our own solar system.
Now, not just the discovery of hot Jupiters, which of course would be the easiest thing to find anyway, but these high eccentricities of a lot of the exoplanets. I mean, if you put it all on the table now with a few thousand known, does our solar system, is it typical? I mean, does it look like an oddball in any way? We had to start by assuming the Copernican principle, right?
Not necessarily. I mean, there may not be any single one typical solar system. I mean, if by something that's, there probably are solar systems that have architectures that are very similar to ours in terms of a similar number of planets and approximately similar spacings. But you wouldn't expect any other solar system to be exactly the same. That said, you could ask the question about, in general, do you expect there to be solar systems with a few terrestrial planets that are the innermost planets at distances roughly comparable, and maybe a few gas giants, anywhere from 1 to 5, let's say, in the outer solar system? Is that kind of typical, in the way we have in our own solar system? And we're only now just being able to find out the answer to that. The hot Jupiters, which are giant planets very, very close to their stars, 20 times closer to their star than Earth is to the sun, are the easiest to discover and the easiest to characterize. And so that was kind of the low-hanging fruit.
Right.
As it turns out, hot Jupiters are not typical. Maybe only 1% of stars have hot Jupiters around them. And so, in a sense, that's more atypical. It's just that they're so easy to discover and so easy to characterize that we're really capitalizing on that. In contrast, Jupiter, which takes of order 10 plus years to go around the sun, and Saturn, which takes of order sort of 30 years, we're only now getting to the point where we can discover planets at those distances. They're cold enough, they don't radiate well, yet they're still close enough to their stars that they're hard to image directly. And so most of the planet techniques that we're using aren't so good for planets at that distance. If you want to use the standard method of so-called radial velocity, namely you imagine just observing the star, watch the spectral lines in the star shift in wavelength slightly due to the Doppler effect. In other words, the planet swings around the star, it forces the star to wobble, and there's a slight blue shift and a slight red shift. In order to use that technique to discover a planet, you have to observe the planet for at least one full planet orbit, preferably two. So if you want to discover Saturn, you need at least 30 years of quasi-continuous data. And we haven't really been observing planets with that technique for 30 years yet. So it's only now getting to the point where we're starting to be able to find out, if planet solar systems like ours are typical. My guess is that in broad outline, there are many, many solar systems that are analogous to the one we have.
And the multiplicity of planets, as well as their particular architecture, that's just going to also be a highly variable number, presumably.
I would think so. There are some studies suggesting from observations that systems around other stars are what you might call closely packed, in the sense that if you were to do a thought experiment of adding an additional planet to such a system and ask the question, would that additional planet be stable? The answer is often no. We can study that with models. We can take observed systems where there are multiple planets and then perform numerical experiments using orbital dynamics models where you actually add a planet like that and see what happens. And there are many known cases of multiple planet systems where if you do that, the additional hypothetical planet is not stable and flies out of the system or leads to a collision or some major reorganization of the other planets. And so that suggests perhaps that initially there may have been other planets in those solar systems that indeed were thrown out. Bringing solar systems to the point where they have just as many planets as they can tolerate and not more and maybe not less.
I'm thinking of something you said about the field astronomy and planetary science getting closer together. There's another interesting thing on the horizon with exoplanets, that as we get to characterization, people are actually starting to talk meaningfully about the atmospheric physics and the geophysics of those planets, and that's another bridge to your field, because now we're actually going to have more than a couple of numbers per exoplanet.
That's right. In fact, I'm not only solar system, over 2/3 of my research is on exoplanets. And so for myself, for example, I take models from the main part of my research. I take atmospheric circulation models that were first developed in the Earth community, which I then ported to Jupiter, Saturn, Uranus, and Neptune to see how they fare in that context. And when you find that you can actually have a model that reproduces those 4 planets pretty well, take that model and then study what would happen if that planet were super close to its star and getting blasted with starlight and, like a hot Jupiter is. And so I agree that the flow back of knowledge back and forth between the different fields is key. I myself have found that most of the major insights that I've been able to contribute in my own research are, in a sense, building on the legacy from not only solar system work, but even Earth work.
Right.
The field, for example, of Earth climate studies and atmospheric dynamic studies is much more developed even than that of understanding, say, Mars or Jupiter. There's a 70-year history of understanding the theory of how the atmospheric circulation works developed for Earth. That understanding is deep but narrow, in the sense that it was applied specifically for the Earth, and most practitioners in that field are not interested in other planets. But it's sophisticated enough that with modest work, it can be extended to other planets. And I've found great fruitfulness and joy in doing that. And
you're also in the great situation that in the quality of data of the exoplanets, there's going to be a pixel or two's worth of data, so you can degrade the details of your models.
Yeah, exactly. Well, it puts you in a position of not having to worry about putting every bell and whistle into your model.
Right.
So from a certain point of view, you could say you have to use cruder models, but that allows you to focus on models that are stripped to their essence, where you can really understand dynamical mechanisms. And for any given planet, there's not much data, But we have many, many planets, and we can see trends emerging that allow us to do studies in a different way. Mm-hmm. That, for example, there are many hot Jupiters now where we are obtaining light curves, where as the planet orbits its star, during one part of the orbit, the day side faces Earth. During another part of the orbit, the night side faces Earth. And if the day side and night side have different temperatures, they're going to glow with different amount of brightness. Mm-hmm. And so we'll see kind of a sinusoidal type up and down nature to the flux we get on Earth, as measured here at Earth with telescopes. And so we can learn from that the temperature difference between day and night on these planets. And so we see trends where, for example, the hottest of the planets have massive day-night temperature differences, and mm-hmm. cooler planets have smaller day-night temperature differences, which suggests that the mechanisms that regulate the temperature difference on planets, which are very effective, for example, on the Earth, in keeping the temperature differences between one side and the planet and the other rather modest, that those mechanisms actually break down when you get to the hottest of the hot Jupiters.
I see.
And so we can actually learn about mechanisms that are operating in our own atmosphere here on Earth and in other atmospheres in our solar system. It can really push them to the limit and see the envelope where they start to break down. So that's something that, even though there's not much data on hot Jupiters, these sorts of trends are really allowing us to, I think, push the boundaries of atmospheric dynamics, and likewise geophysics and other areas, past the confines of the solar system.
Mm-hmm. Well, let's talk a little about the solar system, because I know the giant planets are close to your heart, and people might think, well, we know quite a lot about the giant planets. There can't be any mysteries there or things that are still interesting to study. So talk about some of the good research issues.
Oh, there's lots of puzzles. So on Earth, I think it's fair to say that if you think about the circulation, for example, we understand pretty well what the mechanisms are. There's still questions, lots of people doing climate research, big questions about mechanisms for how things will change with global warming and what controls ice age cycles. But just if you think about the modern circulation in kind of a day-to-day sense, that's pretty well developed. Mars is similar to Earth. It has a similar rotation rate, similar axial tilt. It doesn't have oceans, and it's got a thinner atmosphere, so there are differences. But basically, if you take an Earth model, tweak the parameters to make it more Mars-like, you pretty much explain the weather on Mars pretty well. So there's not a lot of surprises there. That does not work so well if you take that similar model and put it to Jupiter.
Right.
And so there's still lots of puzzles. These are bottomless atmospheres. They're made of hydrogen. Water can condense, but not only that, there's other things like ammonia that can condense. Ammonia even reacts with H2S in the atmosphere to form a salt called ammonium hydrosulfide. There's lightning in the clouds. We don't really understand how the weather works. The weather...
is this, just as an aside, is this beyond the realm of lab physics and lab experiments?
The basic mechanisms are somewhat amenable to lab physics, but only in a limited parameter range. Mm-hmm. For example, you can imagine doing a rotating experiment with water in a tank, and that does allow exploration of certain processes, the formation of jet streams and
persistent
circulation.
Red spot.
Yeah, exactly. But water and on laboratory scales is rather high viscosity, and it's hard to really get into the correct parameter regime. Mm-hmm. But thinking about basic questions, for example, we do not still, despite the Galileo probe data, know what the water abundance in Jupiter's interior is. That's a key thing that's really crucial to our understanding of how Jupiter formed. Mm-hmm. And that links up to this whole question of formation of giant planets in general for other solar systems. We do not understand well the formation mechanisms and maintenance mechanisms for the general circulation. Jupiter and Saturn have numerous east-west jet streams, sort of like the ones we have in our own solar system. But on Earth, we have maybe just one or two jet streams in each hemisphere, depending on how you define them. Jupiter's got about 10 in each hemisphere. So why is that? What controls their width? What controls their speed? Why are there so many? They kind of correlate with the cloud bands that you see in pictures of Jupiter. Mm-hmm. On the other hand, Uranus and Neptune have a much smaller number of jet streams. And also the wind speeds are really fast. So Jupiter has wind speeds that are about triple the speeds on Earth, typically, but it's getting a lot less sunlight than Earth is, and it's radiating a lot less heat to space.
Right.
Usually you think of a circulation as being driven by those processes, the absorption of sunlight and the radiation of heat. So given that that's 20 times weaker on Jupiter than the Earth, why are the speeds of the wind so much faster?
Okay.
One answer is that, well, Jupiter doesn't have a surface, and on Earth, the surface has friction against it, and the friction slows the winds on Earth down. In fact, Earth's winds are among the slowest in the solar system, and maybe that's partly why.
Now, by
you know,
not have a surface, I mean, it's supposed to have a rocky core. We've never seen it, but
yeah, that's a different beast, though. I mean, when you talk about the Earth, I mean, a tiny, tiny fraction of the Earth's total mass, maybe 10 to the minus 6, is in the atmosphere.
right.
Whereas on Jupiter, you're talking about a 320 Earth mass planet that may or may not have up to a 10 Earth mass core.
Right.
So, we're talking about, the measurements that we're taking of Jupiter are, just in the outermost, hundreds of kilometers at the most of a planet with a radius of 70,000 kilometers. Mm-hmm. So it's the tiniest, sort of, all the weather we're talking about, the measurements of that weather are think of an apple and the skin of an apple. That's how kind of deep we're sensing. The core would really be deep at the center, and it's probably not quite so connected to the meteorology. But that does bring up a question about how the weather varies with depth, and we really have no idea. So on an Earth-like planet, the weather just goes right to the surface. Mm-hmm. That's not a surprise because the sunlight goes right to the surface too and helps drive that weather. On Jupiter, the sunlight goes to a pressure maybe a few times that of the Earth's surface, a few bars pressure. But the whole planet goes down to many megabars, millions and millions of bars. And so those jet streams that I mentioned at the surface, we really don't know. There's no measurements right now that tell us, do those die out rather rapidly as you go down into the interior, or do they just cut all the way through the planet? Mm-hmm. And actually, there's a NASA mission called the Juno mission, which was just launched, I'm trying to think when, it was a little over a year ago, I think. Will arrive at Jupiter in 2016, and is a very unusual mission. It will take data that will help to answer that question. So that's even separate from just, scientists arguing with other scientists about mechanisms and so on. That's just like the most basic, zeroth order, unknown, unanswered question about what is Jupiter even like? What is just even the basic structure of the planet, even forgetting what the reasons for that structure are.
And the state of matter way down in there, like red metallic hydrogen, describe what we think the highest pressure, highest temperature interior regions are like.
Yeah. So Jupiter, like I said, it's a huge planet, 10 times the radius of Earth and 318 times the mass of Earth. And it's mostly made of hydrogen. It has a composition similar to the sun, but with all the trace constituents, things like carbon and oxygen, are at a ratio about 3 times what they are in the sun, which still puts them at a pretty tiny fraction of the overall mass. So Jupiter's probably sort of, vast majority is hydrogen. Right. And so when you pressurize anything really, but in this case hydrogen, to very, very high pressure, as you said, it becomes metallic. The electrons delocalize, the electrons can flow around, which means you can have electrical currents. And that's what we really mean by metal. It's almost the definition of a metal. And so that happens at a pressure of about a megabar, meaning 1,000,000 times the typical pressure of the surface of the Earth, which is actually the pressure similar to the pressure near the center of the Earth. And so on Jupiter, though, because it's such a huge planet, those pressures are reached at a relatively shallow depth, maybe 10,000 kilometers into the interior, which sounds like a lot, but it's only like 15% of the way into the interior or something. So of that 318 Earth masses, the vast majority of that is actually metallic hydrogen. Wow. And again, it's totally a pressure effect. If you could somehow take a chunk of that material and pop it up to the surface, it would switch from being a metal back to ordinary hydrogen gas. It's just because it's pressurized. But it is pressurized, and so it's metallic, and so the motions down there are able to generate a magnetic field, just like we have, You
mean by dynamo?
That's right, yeah, exactly. So the magnetic field of the Earth, we think of, and the Earth has a metallic core made of presumably iron, and we think of, bar magnets made of iron. The mechanism that produces a magnetic field in a bar magnet is not relevant to the generation of magnetic fields on planets, typically, because that mechanism breaks down once the temperature is high. Right. The high temperature forces the disorganization of all of the little tiny magnetic fields that like to align in a bar magnet. Instead, the magnetic field in the Earth and other planets typically is generated by dynamo action. In other words, the large-scale convective motions of a liquid conducting metal, iron in the case of the Earth, and a feedback where magnetic field is generated by currents flowing there, cause organization that leads to even stronger magnetic fields.
And you're getting something for nothing, or do you need a seed?
Well, you need a seed, but the end result is not so sensitive to the details of what that seed is, as long as there is one. And so there's lots of models of that for the Earth that successfully produce an Earth-like magnetic field, and even show switches in the pole flips in the sign of the magnetic field like we observe in the Earth geologic record. And so presumably the same mechanism is occurring in Jupiter's interior, and in fact leads to a magnetic field on Jupiter that's much stronger than that on the Earth. So yes, the vast majority of Jupiter's interior, it's hot down there at 10,000 Kelvin, so 20,000 Fahrenheit or whatever, and conditions very high pressure, so very different than what we're thinking about here on the Earth.
Now, as you keep going in beyond that boundary to the metallic hydrogen, are there any other transitions towards the deeper interior, or is it pretty much that same?
That's the main one that's known now. So there are theoretical calculations dating back to the 70s suggesting that this transition to metallic should occur. The exact pressure at which it occurred and the details, such as whether it's a sharp transition or a gradual transition, were a bit fuzzy, and there's lab experiments that one can do where one has a small sample and basically fires in at a gun at huge speeds, kilometers per second, into a target, and that just transiently for just the tiniest fraction of a second produces very high temperature pressure conditions analogous to those inside Jupiter. So from that, we can get both theoretical and observational information just about what the phase diagram of hydrogen is like, even separate from the Jupiter issue. But that then implies that Jupiter's interior is indeed mostly metallic. The main next boundary going in is probably simply this core that you alluded to. Right. So we think probably from gravity data that Jupiter has a core. It's not proven for sure. It's possible to fit the gravity data without having a core, actually. But most likely there's a core.
Could you grow the planet without a core?
Well, that's the question. Most likely not. There's arguments about the so-called core accretion versus direct collapse mechanisms. I'm not sure if you've discussed that in your class, but yeah. So most folks,
And one of the critical, as I understand, one of the issues there is the time scale, which if you have a constraint on the time scale, you think the gravitational instability can do things very quickly. Is that right?
It can, but I think typically my understanding is that most models that do that successfully need to produce something that's higher mass. And part of the problem is that Jupiter and the other planets formed in a disk of material, the solar nebula, which is orbiting the sun. It's not an independent molecular cloud that just collapses into a single star. So you would have to collapse a body like Jupiter in that mechanism in the presence of rotation around the sun in this disk. And there's an inherent shearing, meaning that the part of the gas that's closer to the sun is going to be orbiting the sun faster than the part of the gas that's further from the sun. And that shearing tends to destroy objects that are trying to clump together. So that can be counteracted if you can get a 5 or 10 Earth mass solid body there. Then hydrogen can start flowing onto it, and you can get a runaway. So that's the typical idea for how Jupiter formed. But you could imagine maybe you could form Jupiter that way, and then over the next 4 billion years, erode the core down to nothing. Maybe the turbulent motions in Jupiter's interior could erode that core away, and maybe that core material could dissolve in the liquid hydrogen, for example. And if so, then the absence of a core would not automatically mean that Jupiter did not form a core.
Now, I have to ask, just because it was one of the papers that struck me when I came across it a long time ago, I guess Sagan and Salpeter wrote some, maybe tongue-in-cheek paper about life. There are temperate zones in the Jovian atmosphere where you could potentially have buoyant jellyfish-like creatures.
Yeah, exactly. I remember that from Cosmos when I was in 6th grade.
They were just making a point, presumably. They weren't making a serious suggestion about habitability. I mean, Jupiter is not really habitable in any sense, right?
Well, it's I think not so obvious. I mean, most people would agree that solid planets are probably the better places to look. I think part of the point was that, and this is I think even still a relevant point today, there's been a huge amount of emphasis on what might be considered the classical habitable zone. You imagine Earth-like planets in the early days, in the 60s and 70s, this was envisioned as a rather Earth-like planet, similar atmospheric composition. And you could ask the question, like, over what range of distances from the sun could an Earth-like planet exist and still have liquid water on its surface, which would then, presumably be necessary for life, and so that would define a certain so-called habitable zone, a range of distances where life could exist. And so you get, and then subsequent authors and scientists have broadened the definition. Well, let's not keep the composition Earth-like. After all, Venus has tons of CO2, Mars has a thin atmosphere. Let's broaden the range of maybe possible atmospheric pressures and compositions. And if you do that, then there is a broader range over which you might potentially have liquid water. But still, it's still a rather narrow definition, frankly. And I think part of the point of this paper by Sagan and Salpeter is to say that, look, guys, there are other habitable zones out there.
Can I just push it over?
Sure.
Yeah, I can do that. Rewind to the point of the Sagan paper.
So the point of the Sagan and Salpeter paper is to say, look, guys, there's not just only this classical habitable zone out there. You're thinking in a very kind of Earth-centric manner. There's other possible niches that life could adopt, and it was just making the point that if you list the necessary ingredients for life as we understand them, liquid water, a possible energy source, and so on, that Jupiter has those. That there are clouds of Jupiter which are water, probably liquid water, which have a temperature, even though the surface of Jupiter, the part that we see in images, it's not a physical surface, but I mean the clouds that we see in images of Jupiter are rather cold. But down deeper, there are water clouds where the temperature is actually very similar to the surface temperature on Earth today. And so we have liquid water at the right temperatures. There's lightning, which can cause disequilibrium chemistry. There's sunlight, which causes disequilibrium chemistry, breaking methane and other organics.
And even if the interactions for building complexity are a lot slower than in a true liquid, there's plenty of time to work with.
Exactly, yeah. So, I mean, I don't think people were I don't think they or other people are realistically arguing that Jupiter itself is habitable. Right. It's just more that this is a niche. It is even if Jupiter is not habitable in that way, it is a possible niche.
Right.
And maybe a slightly more serious possibility is that it turns out that many of the moons of Jupiter and perhaps the other giant planets have oceans in their subsurfaces.
Right.
And models suggest that, depending on the exact chemical compositions, even Pluto and Kuiper Belt objects in some cases might have today liquid water oceans in their interiors. And if so, that basically blasts out of the water the whole concept of the habitable zone and means that the entire solar system basically is a habitable zone.
Right. So that's great that you went there, because that was the topic I wanted to get to, the moons of giant planets in our solar system and in general. So again, people who don't know too much about it, have seen them as little blobs in the early images, and they don't quite realize how distinctive and interesting the moons of giant planets are in our solar system. So, paint some pictures of why these are fascinating worlds in their own right.
Yeah, so
and not just airless rocks, blasted by craters, end of story.
Yeah, well, so if you look at the Galilean satellites, for example, which were discovered by Galileo in 1610, it's Io, Europa, Ganymede, and Callisto, they're all pretty large bodies. In fact, Ganymede is the biggest moon in the solar system, and it's actually bigger than Mercury and Pluto. If it were orbiting the sun, there's no question it would be considered a planet. And it turns out it's just as interesting as any planet. The fact that it happens to be orbiting Jupiter than orbiting the sun does not make it in any way less interesting. And in fact, it's almost a miniature solar system in its own right. So each of these four moons have very distinctive characteristics. Maybe moving outward, going from outward to inward, Callisto is rather battered and cratered on its surface, so is perhaps the closest to being geologically dead. Ganymede is similar in size and mass and density to Callisto. However, 2/3 of Ganymede's surface has been completely resurfaced. It's covered by grooves and is totally torn up by internal geological tectonic processes, where the crater densities are very low, suggesting that the ancient cratering record was erased by this activity. Well, that's a puzzle in its own right. We really don't understand how that occurred, or why it would occur on Ganymede and not Callisto, since they're both very similar in size to each other.
Right.
Most models would suggest that if you would produce such activity on one moon, you'd produce the same activity on the other. So that's a puzzle. Moving in,
and I guess there's an obvious extra heating source compared to a similar sized object in the inner solar system, just from the giant planet and tidal heating and so on. Or do you need more than that?
So actually I've worked on that subject myself. So Callisto is not in an orbital resonance, meaning it's just kind of, from an orbital point of view, it's just by its lonesome, and it's not, no of the other moons are really affecting it in a way that matters for geology. Whereas Io, Europa, and Ganymede are locked in an orbital dance called the Laplace resonance, which is a configuration where every time Ganymede goes around Jupiter once, Europa goes around Jupiter twice, and Io goes around Jupiter 4 times. This integer relationship means that that when the moons pass each other, for example, every time Io sort of zooms past Europa in its orbit, that event occurs at a similar point in space.
Mm-hmm.
Whereas if the periods of the orbits are kind of random, those so-called conjunctions would occur kind of randomly.
Mm-hmm.
If they're random, then the geologic kicks that one moon gives the other when they pass each other cancel out. But and when you have this orbital resonance configuration, what that means is that since those conjunctions are happening at the same place over and over again, those little gravitational kicks add up, and they make the moons of they make the orbits of the moons eccentric, so the orbits become kind of an oval shape. And what that means is that if the shape of the orbit's like an oval, then every orbit the moon is getting closer to Jupiter and then farther from Jupiter, and the strength of the tides change. So, of course, we're familiar with tides here on the Earth.
Mm-hmm.
We have an ocean tide that's a few feet tall typically. It turns out that the moon also raises on the Earth a tide literally in the solid Earth itself.
Mm-hmm.
That's smaller than the ocean tide because the Earth is strong and the rigidity resists the tendency to flow up into a tide. But literally, the Earth's solid material oscillates every day in a tide about 30 centimeters or 1 foot tall.
Wow. And I've read there's slightly higher probability of earthquakes at new moon than full moon, or by a few percent or something.
Say that again?
Slightly higher probability of earthquakes at full and new moon.
I
Maybe
haven't heard of that.
significant.
Yeah, I'm not sure. That's a good question.
Okay, so we got land tides, and that in these highly elliptical orbits or moderately elliptical orbits around a very massive object, that's a fair amount of heating.
That's right, exactly. And so Ganymede right now is not being tidally heated in the Laplace resonance, but there are, and it turns out that, and this is something I've worked on, that there are paths toward assembling the system toward the current state in which the system may have gone through an ancient resonance that did pump up Ganymede's eccentricity and did lead to a lot of tidal heating in Ganymede.
Mm-hmm.
So that, in my opinion, provides the best explanation for this dichotomy between Ganymede and Callisto. That even though Ganymede has no tidal heating now, maybe a few billion years ago, it did experience a burst of internal heating that caused massive melting, maybe caused the satellite to expand as phase changes occurred in the interior. And there were, as a result, stresses on the surface that grooved up the surface.
Wow. And are there similar phenomena in the Saturnian moons or not?
There are, yeah. So, for example, Enceladus has been heavily reworked. Some parts of Enceladus are heavily cratered, but other parts are very active. For example, the south polar terrains of Enceladus are active now. There's a jet of material shooting off into space, shooting fine icy particles and water vapor into space. And that's actually feeding one of Saturn's rings, the so-called E-ring.
Is this associated with the tiger stripes, or is it?
It is, yes. These jets are emanating from the tiger stripes, which are 4 fractures lined up in parallel at the South Pole. And the temperatures along those tiger stripes are huge. There's a massive amount of heat pouring out of those tiger stripes, probably, and it's known that the particles jetting out of that jet are salty, which provides pretty good evidence that they're coming out of a source of liquid. Mm-hmm. They're not just kind of sublimating off of a solid chunk of ice. They're literally boiling off of out of a liquid reservoir.
And to what you said before, if Enceladus is the size of Rhode Island or something, so if that can be, that's got the ingredients for habitability too.
That's exactly right.
You would never have noticed.
That's right. That's right. It's a huge puzzle. I mean, the radius of Enceladus is 10 times smaller than the radius of Ganymede. It's 100 times smaller surface area, and it seems like it ought to lose its heat pretty fast, but somehow it's managing not to. And exactly right. That's a possible abode for life right there.
And I know you've done the modeling that sort of cements this view, but it's also surprising to a lot of people that some of the larger moons that they do have cratered surfaces. They don't seem to hold any significant atmospheres. There still could be liquid water under the surface, right?
That's right. So it turns out that ice and water behave differently than most materials. For most materials, like rock, the kind of silicate rock that Earth's outer layers are made of, if you make it at higher pressure, then the melting temperature is larger. Whereas with water, it's the reverse. So the higher the pressure is for ice, the easier it melts. And so what this actually means is that down in the interior, it's easier to melt the water than it is if it's at the surface. Easier to melt the ice than if it's at the surface. And also, of course, ice is less dense than than liquid, and so the natural configuration is to have the ice floating on top of the liquid.
Mm-hmm.
And ice is a great insulator. And so if you form an ocean down there at a depth of tens of kilometers or more, it's not going to lose heat that fast, frankly. It's not like having an ocean on the surface of the Earth that just radiates massive heat to space and would just instantly, get frozen up. This layer of ice, this ice shell on top of the oceans, is a great way of preserving the ability of the oceans to stay alive.
And did this only be, I mean, we've had, satellites looking at these moons for a few decades, but the modeling or the understanding that the liquid could be there, it's more recent, right? The modeling only got good enough to say that.
It is, yeah. There's been lots of evolution in the modeling. The early models from like the late 70s to the early 80s, it was actually funny. If you write a list of all the papers published from like the late 70s to say the late 80s on the subject of whether Europa has an ocean, they almost alternate. Yes, no, yes, no, yes, no. There's about 10 total with like 5 in each camp, right?
Right.
And so the first model's, oh yeah, well, if it's just a conductive shell that just conducts its heat out, then it can easily maintain an ocean. Next guy, well, no, maybe it's convecting, which is a more efficient way, that literally the solid ice itself is convecting and moving, and no ocean. Next guy, well, no, you overestimated how fast that process should make it lose heat. There is an ocean. Mm-hmm. Back and forth. Nobody could decide. And actual data on that subject did not come until Galileo, the Galileo mission, which was started in 1995. And the evidence, interestingly, was not just from the surface record, but from magnetic fields. Mm-hmm. The surface of Europa is very disrupted, even more than Ganymede. It has very few impact craters. It's a bunch of just ridges and geologically disrupted terrains, clearly very active geology. Some folks had made the argument that implies an internal ocean. You need to have an internal ocean to make it easier to disrupt all that stuff on the surface. But that is not really a cut and dried point. People were arguing that back and forth. Maybe just having a solid ice shell is good enough if that ice shell is soft. Mm-hmm. And so the real evidence actually is the fact, is magnetic field data. An ocean, if it's salty, is a conductor. Salty water is an electrical conductor. Salty ice is not such a good electrical conductor because the salt grains are sort of isolated from each other and they can't pass electrons back and forth. Right. And Jupiter itself, as we discussed, has a very strong magnetic field. And it turns out that Jupiter's magnetic field, like on the Earth, is tipped from its axis of rotation. And so what that means is that the magnetic field is flipping and flopping around, varying in its, tipping around on its axis every Jupiter day. And so the strength of the magnetic fields, as seen at any of the moons, is changing over time, pretty much wobbling back and forth every Jupiter day. And anybody who studied basic physics knows that if you have an electrical conductor, like a metal, say, in a time-variable magnetic field, then electrical currents will be induced that will induce a magnetic field that attempts to cancel out the time variations in the imposed field. And so we have detected signatures exactly like that at Callisto, Europa, and possibly Ganymede. There's an interesting political story, which is that I was in grad school while this was happening, and this measurement was done first at Callisto. Mm-hmm. And so there was a flyby of Callisto that showed, oh yeah, Callisto has a small magnetic dipole and a certain orientation. It was consistent with the magnetic induction effect. But maybe there could be just a fixed dipole also from a dynamo or something. But then another flyby later showed that the dipole was in a different orientation. Again, exactly what you would expect for the induction model, which pretty much disproved all the other models and proved the induction model. At that point, we did not have similar measurements for Europa, although they did come later. So there was a period of time where we knew for certain that Callisto had a liquid water ocean, whereas we did not know if Europa had a liquid water ocean. And there already at that point had been a huge bandwagon effect of astrobiology on Europa. Right. And as sort of a bright-eyed, bushy-tailed grad student, I just thought it was a very interesting political note that there was not a mass defection of the astrobiological community from Europa to Callisto.
Right.
I remember a press conference where there were lots and lots of very cool results from Jupiter and just the geology of the moons and so on. And the whole press conference basically got hijacked by astrobiology questions about Europa, which are all totally speculative and sort of eclipsed all the cool actual science that was being done on the geology and so on and so forth.
It's interesting, the bandwagon effect. And to sort of put a number on this, because it's a huge implication for astrobiology. As you said, the habitable zone concept is, got to encompass this cryogenic biosphere. But just if you had to put your best guess number on it, how many habitable spots are there, not counting more than one per moon or planet in the solar system? I mean, probably a dozen or so, right?
There could well be a dozen. I mean, so like I said, we know of these oceans on, Callisto and Europa. There's more tentative evidence for one on Ganymede. We know there's liquid water probably on Enceladus, like we discussed. There's probably an ocean on Titan. And then for the other moons, the smaller moons, and then as well the Kuiper Belt objects, it really depends on composition, in particular how much ammonia there is. Ammonia is a great antifreeze, and models have shown that if there's a few percent of ammonia in the ice, then if there's something that causes it melts super easily at very low temperature. And in that case, you could have up to maybe 15 or 20 bodies in the outer solar system with internal oceans.
Wow.
If there is not ammonia in those bodies, then it's much harder to get them to melt. In that case, you may just have the ones that I listed originally, sort of 5 or 6 oceans out there.
But either way, on average, you're talking about an order of magnitude tacked onto a Drake equation.
Yeah,
in its simplistic form.
And not only that, if you think about it, that probably means there are more habitable niches in the outer solar system than there are on the terrestrial planets in the inner solar system, which is pretty striking and humbling if you think about it.
Which also makes you want to push exoplanet. You want to be able to find large exomoons, which I presume is beyond the pale right now.
It's hard to do, but yeah, people are trying.
So this has been fun. Let me ask you one last question.
Sure.
So, blank checkbook, you can write your $1 billion, you can write your own mission, outer solar system mission, completely of your own conception. Where would you go? What would you want to do?
Oh, gosh. Cassini is so great at Saturn. We're going to have missions that are already on the books to Jupiter, hopefully. It'd be great to have a Europa mission like the one that's currently sort of on the shelf in the U.S.
Although they seem a little timid to me. I mean, we're not landing, we're not melting through the ice and sending hydrobots. We're not landing on Titan and bouncing around the lakes. So
they're being timid probably because they were being forced to by modest budgets.
Okay, well, put as many.
But yeah,
make it big. Make the check as big as you want. What's the most exciting thing you could do? You would want to do with a mission if you could write the ticket?
You know what? I'm going to go with the idea that we've already got a Jupiter mission that hopefully will really happen, and Cassini's at Saturn, and so I'm going to blast past that and pick a mission like that at Neptune.
Okay.
I like Neptune. Neptune's cool. The interior of Uranus and Neptune is totally different than Jupiter and Saturn. They're sometimes called ice worlds, which is a little misleading, but is intended to convey the idea that their interiors are pretty much water. So in some sense, you could think of the interiors of Uranus and Neptune as being oceans. It's hotter and probably ionized and mixed with other things, so it's not quite like an Earth ocean, but it's pretty amazing. And they've got, super fast winds in their atmospheres, powered by sunlight that's 0.1% of what we have on the Earth. They've got moons like Triton orbiting Neptune with a temperature of 40 degrees above absolute zero, yet is more geologically active than the vast majority of bodies in the solar system.
Wow.
And we just do not understand what is going on there. And we'd love to know the composition of the planet itself. I'd love to send a probe into the atmosphere and interior of Uranus and Neptune. How much carbon is there? How much oxygen? What's the ratio? What's the chemical species? And really learn how this class of body, which is intermediate between a gas giant like Jupiter and a terrestrial planet like Earth, how does such a planet form? I think there'll be lots and lots of lessons for our own solar system as well as for exoplanets.
Great. Well, you sold me. I mean, and not only the money, but it's good you're a young guy because these missions take a couple of decades.
They do, yeah.
Right? Okay.
They do.
Thanks a lot, Adam.
Thank you very much.